Okay, this is a recording of the 1-3A worksheet, starting with problem number 2. For exercise 2 and 4, graph the function, state the domain and range, and list any intercepts. So on this particular problem, I started out with an e raised to function. Know that if it's an e raised to, you're probably going to have to use your calculator to get some values, but there's always one good value you can get out. Remember the most interesting value of x. What makes the argument equal 0? E raised to the x, the argument is simply x. So if I plug 0 in, e to the 0, don't forget, is 1. 1 plus 3 is 4. But then to get the other points, if we plug 1 in, we get e. Hopefully you know e is 2.71. 2.71 plus 3, you can do that without a calculator and get 5.71 just to get an approximated value. If I plug 2 in, I get e squared. Now that's a little bit more complicated to think 2.71 squared. I know it's some number between 2 squared and 3 squared, so we can still approximate a little bit, but it turns out to be this value right here. And then if I plug in -1, realize e to the negative first power is 1 over e. So really, this is between 1/2 and 1/3. It's actually closer to 1/3. It's that close to 1/3. It's 3.368. And if we plot those 3 points, we can sketch this graph. Now, you could have plotted more points, and I probably would expect that if this base was 2 or 3. But in this particular situation, since the base is e, I wouldn't expect it. But what we do have to know is that we have a horizontal asymptote whenever there is a constant added to an exponential function. And y equals that constant will be our horizontal asymptote. So when we come down and look at this, the domain of this exponential function is all real numbers. We can plug anything in for x. Here's how it's written in interval notation. The range, however, for most exponential functions is going to be typically either above or below that horizontal asymptote. In this case, it's above that horizontal asymptote. It will not hit the horizontal asymptote. It gets closer and closer and closer to it. That's why the horizontal asymptote is y equals 3. A horizontal line is y equals a number. And the range is y is greater than 3. The y values are above that horizontal asymptote. Here is set builder. Here is interval. Okay? X-intercept. You plug 0 in for y. If you subtract 3 to the other side, you cannot take the natural log of a negative number. That's why there is no x-intercept. Look, this graph never crosses the x-axis. But a y-intercept can always be found by simply plugging in 0 for x, and we did that right here. Problem number 4. Now this is a lot better because we have a base. One thing that we have to recognize with exponential functions, the base cannot be negative. So when we look at this, we have to recognize this is not -2 raised to the negative x power. This is 2 raised to the negative x power, negate it. That's how we read it. Remember, exponents are lazy. They're only going to do exactly what it's told to do. And in this case, there are no parentheses around that -2. If there were, this is not a function. It wouldn't work because we cannot take a negative number raised to, for instance, the 1/2 power. So it will not be a nice function. The base always has to be positive. So when you see this negative out front, realize you're raising to the exponent first and then just simply negating that number. Let's start with this. We know the horizontal asymptote is y equals that constant. And dot that in. Dot, 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 dot. Now we can point plot. Most interesting value of x is 0. But here's how we have to read this. 2 to the 0 is 1. Make it negative. -1 minus 1, that's how we get -2. 2 to the negative first when I plug 1 in. I cannot evaluate negative exponents until we make it positive. You make a negative exponent positive by moving the base to that exponent to the denominator. So the base of 2 goes down to the denominator to make the exponent positive. 2 to the first power is 2, so it's -1/2. minus 1 is negative 1.5. If I plug in 2, 2 to the negative second power is 1 over 2 squared. That's 1/4. Make it negative. Subtract 1, negative 1 1/4. Let's do one more just for good measure. 2 to the negative third power is 1 over 2 cubed. That's 1/8. Make it negative. Subtract 1, negative 1 1/8. Being able to evaluate negative exponents that quickly is going to be important throughout the entire year as we get into more of the calculus evaluation concepts. Look what happens when we plug in negative 1. Negate negative 1 becomes positive 1. 2 to the first power is 2. Make it negative is negative 2. Subtract 1 is negative 3. 2 raised to the negative of negative 2 becomes positive 2. 2 squared is 4. Make it negative. Negative 4 minus 1 is negative 5. Negate negative 3 is positive 3. 2 cubed is 8. Make it negative. Subtract 1. So I'm always going to talk through this computation with you because a lot of times it's the computation that can create problems for students. We plot those points and we recognize that the larger the x value became, the closer this value is getting to negative 1. As a matter of fact, if we would have done 4, we would have gotten negative 1 and 1/16. Right? We'd get even closer to it. It's getting closer and closer and closer to that horizontal asymptote. So, domain, again, is all real numbers. We can plug anything in for x. There it is in interval notation. The range, this time y is less than negative 1 because of that negative coefficient that was put out front of that exponential function. It reflects it in the x-axis. Here's how it's written in interval notation. Remember, always parentheses on infinity and negative infinity. It's a parentheses here because it never hits that horizontal asymptote. There's the horizontal asymptote. Again, there is no x-intercept because if we plug in 0 for y, we add 1 to the other side, we'd have to get the negative to the other side, and I cannot take the natural log of a negative number. And we can see from our picture, it never crosses the x-axis. Problem number 6. These are nice little quick problems, and I like them because we do try to do this to simplify. It's nice to write an exponential expression using the smallest base possible. And on these problems, they're telling you what base to use. 16 is the same thing as 2 raised to the 4th power. 2 times 2 times 2 times 2 is 16. So if I replace 16 with 2 to the 4th power, now I'm just going to use my exponential rules that were presented in Algebra 1, and again in Algebra 2, and again in pre-calculus. Exponent raised to an exponent, we multiply the exponents. 4 times 3x is 12x. There it is. This one is a little bit more tricky because 1 over 3 cubed. 3 cubed is the same thing as 27. They tell me to rewrite as a base of 3. But now I have to bring that 1 over 3 cubed up to make it 3 to the negative 3rd power. Remember, just like we did before, if we had a negative exponent, we could move the base down and change the sign of the exponent. Same here. If we have a base and a positive exponent, we can move it to the numerator. We just have to change the sign of the exponent. Now we have an exponent raised to an exponent. You need to multiply the exponents. There it is. Problem number 10 and 12. Find the zero of the function analytically first, and then use a calculator to confirm your solution. To find a zero means set the function equal to 0. If we add 4 to the other side, how do I get the variable out of the exponent of e? Well, what is the inverse operation of e raised to? Natural log. Natural log is the inverse operation of e raised to. Now we're going to get more practice with this in section 1.5. But if we take the natural log of both sides, remember, the exponent drops down in front and the natural log of e is 1. Or you can just think of it that the natural log of e raised to, these two operations are inverse operations. So we are left with the exponent of e. Here's the natural log of 4. Now, I did this because this is going to happen a lot on the multiple choice part of the AP test. If they can put in one more mathematical operation, they like to do it. So 4 is the same as 2 squared. And then they'll drop down this 2 using the rules for logarithms. We're going to go over those rules in more detail in section 1.5, but you've seen them in Algebra 2 and in pre-calculus. And this is the rule that says the exponent of the argument can drop down to become the coefficient of the logarithm. Here it is. You can type this into your calculator. It's actually easier. Or you can type this into your calculator. In both instances, it will produce this value right here. I'm not going to show that calculator work. You can certainly see me if you have questions on it. All right. Remember, we can also check zeros in our calculator by using the root key or x-intercept 0 key that is under second calc. Okay? Problem number 12. Same idea. Set it equal to 0. In this case, if this is negative, I'm going to add this to the other side, right? I'm going to add this term over here. Now I'm dealing with only positives. The variable is in the exponent. How do I get the variable out of the exponent? In calculus, we only use natural logs. We do not use logarithms. Everything is natural log. You're going to find out as we progress. So I take the natural log of both sides to undo a raised to. Here's where you have to know this rule because this doesn't undo it completely. Now I have to know. When I take the natural log of an argument raised to an exponent, the exponent can drop down and become the coefficient of the logarithm. And again, we'll see it more in section 5. And now this is just a number. It's the natural log of 2. Divide both sides by that number to get rid of the natural log of 2 on this side to create a natural log of 2 on this side. Okay, natural log of 3 divided by natural log of 2. That would be the analytical solution. And sometimes they're just left like this on a multiple choice question. You can leave it like this on a free response question. Don't type it into the calculator. Any numerical representation is correct. Don't make a mistake typing it in. But here is the numerical value approximation in case we need it. 22. Getting into some word problems. Population growth. The population of Silver Run in the year 1890 was 6,250. Assume the population increased at a rate of 2.75% each year. First thing we have to know is this percent is the decimal value 0.0275. There it is. Remember, we're using the exponential growth model, which is the initial amount times, if it's a growth, it's 1 plus the rate raised to the time. In this case, they're giving us everything but the time. I'm sorry, they are going to give us the time here, okay? But we use this rate. Here's the initial amount in 1890. 1 plus 0.0275 is 1.0275. And now we just want to evaluate that after 25 years. From 1950, from 1890 to 1915 is 25 years. We simply plug this into our calculator just like it looks. And we get 12,314. Notice I'm always rounding to 3 decimal places unless they specifically say on the AP test, round to the nearest person, round to the nearest bacteria, whatever it is that you might be finding, always present 3 decimals. Then they want to know in 1940. Well, that's 50 years. Do the exact same thing. I'm just plugging 50 in. In your calculator, once you have this in, by the way, if you hit second enter, it will call this up, and you can just go change this to 50. It's actually a lot easier or quicker to do that if you use the second enter feature on your graphing calculator. There's the population. This is a better question. This is one I was thinking of. Approximately when did the population reach 50,000? That is a lot more than 6,250, right? This time, I want to find a time. This is what I'm searching for. I'm setting this function equal to 50,000. One thing that we have to keep in mind all year long, I cannot take the natural log of both sides until I have a base raised to an exponent only. So we have to divide by the 6250 first. You could cancel the 0. It actually reduces down to be 8. It's 8 times the population. So really they could have asked this question, when will the population be multiplied by a factor of 8? Same thing. Take the natural log of both sides so that I can use my property that says the natural log of a base raised to an exponent. We can drop the exponent down out in front and make it the coefficient of this natural log. This actually becomes the numerical coefficient of t when we do that, when this is the variable. The natural log of 1.025 is a number. Divide both sides of the equation by that number. That is our analytical answer. But we want to know how many years it takes. Type this into your calculator. This definitely needs to be rounded to 3 decimal places. Don't forget units of measurement. 76.651 years. Good. These population growths and growth of money are all great problems. Here's one that's more financial for people who see themselves perhaps in more of a financial career. If John invests $2,300 in a savings account with a 6% interest rate compounded annually, this makes life a lot easier when it's compounded annually. How long will it take John's account until the account has a balance of $4,150? So here it is. Remember the rate is 0.06, so it's 1 plus 0.06 because it's increasing. We're not losing money. It's not depreciating like a car. There's the initial amount. And I want to know, when is it going to go from $2,300 up to $4,150? Divide both sides by that 2,300 because I cannot take the natural log of both sides until I have a base raised to an exponent only. I reduce that fraction down just to make it easier to type into the calculator, but no need to do that. Take the natural log of both sides so that I can drop down this exponent out in front of the natural log, because now this becomes the numerical coefficient of the variable t. It's just a number. It's just written as a natural log, but it's a number. Divide both sides by the natural log of 1.06. This would be the analytical answer. When I type that into the calculator, 10.129 years. Doubling your money. That's always a good thing to do. Determine how much time is required for an investment to double in value if interest is earned at a rate of 6.25% compounded monthly. This throws a wrench into the formula. But I want you to not memorize the formula. I want you to understand why this is the same formula that we're using here with a minor adjustment. Instead of it being the initial amount times 1 plus r raised to the t, if you're getting 6.25% compounded monthly, that does not mean that you're going to get 6.25% every month. I would be in this investment in a hurry if that was the case. If I could get 6.25% every single month on the amount of money in there. It's just compounded monthly. And if it's compounded monthly, I'm really only going to get 1/12 of this rate each time that I compound it. I'm compounding it more. I am going to compound it 12 times t. In other words, if it's 1 year, I'm going to compound it 12 times. If it's 2 years, it's going to be compounded 24 times. But I'm not going to get the full rate 24 times. That money would grow rapidly. Everybody would be in this investment. The rate also has to be divided by 12 because you're going to get 1/12 of that rate each time that's compounded. That's why it's the same formula, but we have to divide the rate by n since we are multiplying the t by n. Hopefully that makes a little more sense so it doesn't have to be a straight memorization. So I don't know what the initial amount is. I'll just call it p. I want it to double. That's 2p. Here's my rate. Here's my compounding. There's my compounding. There's 2 variables, but when I divide both sides by p, the p goes away. Some students want to just start with this. That's okay, but understand why that's happening, because when I divide by the principal, I'm always going to end up with a 2 on this side when it's a doubling. I'll end up with a 3 if it's a tripling. We're going to see that down here. A lot of students get confused actually from this step to this step. Why did I do this? It's just easier to deal with instead of two separate. If I make this 12 over 12, I now have a common denominator. And 12 plus 0.0625 is 12.0625 divided by 12. This is just an easier way. It's one fraction instead of two separate terms. Raised to the 12t. Take the natural log of both sides. Why? Because I am trying to solve for a variable that's in the exponent. Anytime I'm trying to solve for a variable that's in the exponent, I either have to get the bases to be the same, that's always choice number one, or take the natural log of both sides so that I can get the variable on the same level as the rest of the numbers. Because my property for logarithms allows me to drop down the exponent out in front of the logarithm. And we always use natural logs, not logs in calculus. Here's a variable. These are just two numbers. Divide by these two numbers. Divide both sides of the equation by 12. Divide both sides of the equation by this number. It's a number. It's just written as the natural log of a fraction, but it's a number. This is what we have to type into the calculator. Be careful. Make sure you parenthesize the numerator, parenthesize the entire denominator when you type it into your calculator. You should definitely practice this. Don't just look at this and say, oh, that's the answer. Practice. Because if you don't get this answer, it's probably just because you're not typing it in correctly. Make sure you parenthesize the denominator, parenthesize the numerator, whenever these numerators and denominators get more complicated. Okay? And you get 11.119 years. 28, same problem except now we're tripling. So I'm going from P to 3P. Here's my rate. Here's T. And it's compounded annually. So this is a much better problem when it's compounded annually. Divide both sides by P, we get a 3. Take the natural log of both sides so that I can make the variable drop down out in front of this natural log. This actually is technically the coefficient of this variable now, because the coefficient is just a number. It's the numerical coefficient of t. It's a number. Divide both sides by this number right here. Natural log of 3 divided by the natural log of 1.0575. Type that into your calculator. 19.650 years. Now, same problem, except this one is compounded continuously. Compounded continuously, it was one of these things that in the 80s, a lot of the banks were advertising, we compound your money continuously. And it took people a while to figure out that it's really not a huge difference if you compound my money continuously or if you even compound it quarterly. There's a difference. There's a little bit. But really, banks just started compounding everything quarterly. Most do anyways. But here is the formula. It's a little bit different. We don't have 1 plus r as the base. The compounded continuously formula. And we will actually verify this a little bit later on in calculus, using some limits to figure out how we get the value of e. We'll discuss this in more detail. But it is the principal, or the initial amount, e raised to the rt. Sometimes you will see this presented as the amount at any time is a sub 0 e to the kt. Same thing. We typically use that when it's not a money problem. If it's a money problem, we try to be more descriptive by calling this P for principal. We try to be more descriptive by calling this R for rate. That's it. Divide both sides. I want this to triple. So I set it equal to 3P. Divide both sides by P. Now it's the same problem, but even easier than the last one, because when I take the natural log of both sides, that actually undoes the natural log of e raised to. I don't have to drop it down, it just undoes it. Because e and natural log, e raised to and natural log are inverse operations. So I'm just left with the exponent. Divide both sides by 0.0575. Type that in your calculator. 19.106 years. Okay? So think about this. So if it's compounded annually once a year, it's 19.650 years for your money to triple, versus if it's compounded continuously, it's 19.106 years for your money to triple. There's not a significant difference, but there is. It's a little bit faster. 32, eliminating a disease for the future medical people out there. These are great cases, especially at some of the things that we're talking about recently. Suppose that in any given year, the number of cases of disease is reduced by 20%. If there are 10,000 cases today, how many years will it take to reduce the number of cases to 1,000? Well, really, it's 1/10, right? So here it is. Now I'm reducing. The only difference in the formula is if it's a decrease, exponential decrease problem, it's 1 minus the rate. If it's an exponential increase, it's 1 plus the rate. So this is the initial amount, and notice I use A sub 0 now instead of P for principal because it's not a money problem, but they mean the same thing. There it is, it's 10,000. The rate is 0.2. There's the time. I want to divide both sides by 10,000. I get 1/10. 1 minus 0.2 is 0.8. I'm still solving for this variable. If I'm solving for a variable in the exponent, take the natural log of both sides. So I can drop down the exponent out in front of the natural log. This is a number. Divide both sides of the equation by that number. There it is. 10.319 years. Some of you might say, why don't you just convert this to a decimal right away? Why don't you just convert this to a decimal right away? You can. Just make sure that you carry out enough decimals, because you need to make sure that when you take this number divided by this number, your answer is accurate to 3 decimal places. If it is not, you will not receive credit on the AP test. So be careful that you do not round too quickly. Okay? That would be my biggest fear. And sometimes the answer is just presented analytically. So on a multiple choice problem, I think it's good for us to practice these answers that are expressed analytically. All right, to eliminate the disease, that is to reduce the number of cases to less than 1. Well, you can't really write less than 1, so we just set it equal to 1. Okay? How long is it going to take to get down to 1 case? Because then we just have to wait for that case to be eliminated. Same thing, divide by 10,000, take the natural log of both sides, and divide. Notice, to reduce it to 1/10 is 10.319 years, but to reduce it all the way down to 1 case is 4 times that time. It's kind of an interesting problem, especially when we're talking about some of the issues in this year of 2020, right? Bacteria growth, another great one. This gives you the model completely. It already gives you the rate. Okay? And it actually should be, I typed this up wrong, so when I write this right here, use this value instead. And if you did it with this one, it's fine. But in the book, it was supposed to be 0.693, and you can see that I transposed these two numbers when I was typing it. Sorry about that. What was the initial number of bacteria present? If you plug 0 in for the time, e to the 0 is 1. 1 times 100 is 100. That's why this value right here is always, right here, this coefficient is always the initial amount, as long as no number is being added or subtracted to it. How many bacteria are present after 6 hours? I just plugged 6 in. Type this into my calculator. 6,394. That's a lot. We went from 100 to 6,394 bacteria. And again, I present 3 decimal places. It did not say to round it. Approximately when will the number of bacteria be 200? Well, I know it's going to be between 0 and 6, right? 6 is a lot more than 200. So if I set this equal to 200, divide both sides by 100, take the natural log of both sides so I can drop down this exponent. And notice here, I just get rid of the natural log of e because the natural log of e is 1. I can divide both sides by 0.693. Natural log of 2 divided by 0.693 is 1.002 hours, which we can then round that to 1 hour. It's about 1 hour for the bacteria to double. It's doubling in an hour. All right, true false on this particular section. The number 3 to the negative 2 is negative. Sometimes students think this is true. It is not. The exponent becomes positive when I drop the base down to the denominator. The number does not become negative. It's 1/9. That is false. If 4 to the 3rd power equals 2 to the a, then a equals 6. Well, that's not true. 4 is 2 squared. Exponent raised to the exponent is 2 to the 6th power. Oh, this is true. A equals 6. That's how we would verify it. Don't solve this one by taking the natural log of both sides. Our first course of action is always to see if we can get the bases to be the same. And in this case, we can. So now we can just say, well, 2 to the 6th has to equal 2 to the 6th. A has to be equal to 6. So if you can get the bases to be the same, you can set the exponents equal to each other. And this will happen occasionally on an AP test, that you can solve it much more quickly and without a calculator by simply getting the bases to be the same. That's why I showed it this way. And this is true. 43. John invests $200 at 4.5% compounded annually. About how long will it take his investment to double? Here it is, 1 plus the rate raised to the t, start with 200. I really wouldn't even have to write this in. I know it's doubling. P, 2p would have been fine. When I divide, I'm going to get 2. I have to divide first because it has to be a base raised to an exponent only before I take the natural log of both sides. Drop down the exponent, which is the variable I'm searching for. I can't solve for it until I get it down on this level. Now take the natural log of both sides, 15.747, or roughly 16 years since they rounded it. Okay, on problem number 44, this asks for which of the following gives the domain. Don't be fooled by this. Domain, I can plug anything in for x. It's not asking for the range. Some of these are trying to gear you towards a range. This is the domain. And I can plug anything in. E raised to any value works. Even e raised to the 0 is 1. The domain is all real numbers. Notice this is how we write it in interval notation. I wrote it for you in set builder notation as well, just as a reminder. Eventually we'll be able to drop the set part of this and just write x is the element of all real numbers. Or write out all real numbers. Do not put ARN as an abbreviation. It will be marked wrong just because I've never seen it on any rubric for the AP test. Which of the following gives the range? Now that's a little bit different. Remember, this is a horizontal asymptote, y equals 4. I just got to determine, is this exponential function going to be above or below this? Well, I'm subtracting these values from 4, so my y values are going to be below it. And I actually tell you this is the horizontal asymptote, plot a few points so that you can see the y values are below the asymptote, but you should almost be able to picture it. Therefore, the range, y is any real number such that y is less than 4. That's set builder notation. Eventually, you'll just be able to say y is less than 4. But notice, a lot of the multiple choice are going to be in interval notation. Parentheses on, negative infinity, comma 4, parentheses, not a bracket. 46, last problem. Which of the following gives the best approximation for the 0? Here's the work. Whenever it asks for a 0, you set the function equal to 0. We actually did this problem already. I add this to the other side, take the natural log of both sides to do the e, undo the e raised to. I showed the work here so you can see it's the same rule. The exponent comes down out in front of the natural log. The natural log of e is 1. You need not show these steps. You should know that the natural log of e raised to is going to produce an x right away. You could have went right from here to here. But I want to show this so everybody understands why that is true. And x equals the natural log of 4. Could be presented this way. Sometimes on multiple choice it's presented this way. We already talked about it. Either one, you type into your calculator, you get 1.386. So don't get frustrated when I do this. A lot of times I'm just trying to show you that this answer could be presented in multiple ways in its analytical form. Okay, we're done with this one. Good luck on the assignment. Hopefully it went well.